Good morning, everyone. I am Mauricio Castillo from the Pontificia Universidad Católica de Valparaíso, Chile, and I will present the work titled An Autonomous Galactic Swarm Optimization Algorithm Supported by Hidden Markov Models. In this presentation, we will review the following topics. 1. The set covering problem. 2. The particle swarm optimization algorithm. 3. The Galactic Swarm Optimization algorithm. 4. The binarization technique used. 5. The Hidden Markov Models for PSO state deduction. 6. The parameter optimization method implemented. 7. The results obtained solving the SCP problem. 8. The conclusions of this work. And 9. The summary of the contents review. The set covering problem is a binary optimization problem that proposes the installation of some service in different locations, with the condition that an entire area is covered by the service and trying to minimize the installation cost. An example could be the installation of fire stations in a certain geographical area, where the installation at one point represents a specific coverage, as shown in the image. The problem is solved by covering the sun completely, and one solution is better than another if the installation cost is lower. The particle swarm algorithm proposed in 1995 by Kennedy and Eberhard is a population heuristic that simulates the movement of a flock of birds in search for food. The algorithm contains a certain number of particles and its movement has three components. 1. Cognitive component. Each particle is attracted to the best position it has historically taken. 2. Social component. Each particle is attracted to the particle with the best position. 3. Inertial component. Each particle experiences a moment of inertia that keeps it on its original trajectory. Each of these components are controlled by three parameters known as the acceleration coefficients C1 and C2, which indicates the confidence each particle has in its own path and the neighbors, and the inertial weight omega, which indicates the amount by which the previous velocity of the particles affects its motion. The Galactic Swarm Optimization algorithm was proposed in 2016 by Butanakarjan as a way to run several PSO in parallel. The algorithm works on two levels. The first one works with a certain number of PSO independent from each other. The second level is created from the first one by selecting the best particle from each PSO in level 1 and creating a new PSO. The algorithm aims at obtaining a better balance between exploration and exploitation during the search process, where level 1 represents an explorative behavior and level 2 an exploitative one. Since the GSO algorithm works in the domain of real numbers, it is necessary to use a process that allows us to solve the set covering binary problem. The process used is called the two-step binarization. The first step is to transfer each real value to a real domain between 0 and 1, and then a binarization function transforms it into 0 or 1. This process allows us to use the GSO algorithm to solve the set covering problem. To improve the performance of the algorithm, we will control its parameters, guided by the state of each PSO that is executed by GSO. We will do this based on a diversity metric known as evolutionary factor, which reflects the position of the particle with the best fitness value compared to the rest of the particles. The evolutionary factor is calculated by obtaining the average distance of each particle from all others, distinguishing the particle with the shortest distance, the longest distance, and the average distance of the particle with the best fitness, according to the equation shown. The value of the evolutionary factor varies according to the position of the best particle, decreasing when the best particle is close to the center of the PSO and increasing when it moves away. Based on the configuration of the particle position within a PSO, we will distinguish 4 possible states. Exploration. The PSO particles are at a similar distance from each other, scattered in the search space without finding yet a promising area. Exploitation. The particle starts to follow a particle that has found a promising zone. The distance between the best particle starts to decrease compared to the others. Convergence. All PSO particles are following the best particle, which is in the center. In this state, the particles are very close to each other. Jump out. A different particle from the best one finds another more promising zone and moves away from the group that was converging, becoming the new best position. The 4 states can be modeled as a Markov chain, as shown in the figure, where the arrows indicate the possible transition between states. The Hidden Markov model is a statistical model that allows us to classify a series of observations into hidden states, modeled as a Markov chain. The Hidden Markov model is able to solve 3 tasks. 1. Likelihood. Given a set of observations, determine their probability of belonging to the Hidden Markov model. 2. Decoding. Given a set of observations, determine the most likely chain of hidden states. 3. Learning. Given a set of observations, update the internal parameters of the Hidden Markov model to maximize the likelihood of the observations. The Hidden Markov model allows us to classify the evolutionary factor of a PSO into one of the states in the Markov chain using task 2, where the evolutionary factor represents the observations and the Markov chain the hidden states. In addition, at each iteration, the Hidden Markov model is able to learn from the observations to improve its deductions. We will give an example of the functioning of task 2 for the deduction of the states of a PSO in 5 iterations. First, we have some evolutionary factor data calculated for 5 iterations. The version of Hidden Markov model we use requires discrete observations values, so we transform the values according to the table on screen. The Hidden Markov model has 3 parameters. Matrix A indicates the probability of transition between states. Matrix B indicates the emission probability of each element observed for each hidden state. The initial matrix pi indicates the probability of one of the states occurring at the beginning. The Viterbi algorithm is in charge of solving task 1 and 2. For the first observation, we will calculate the emission probability of the observation at each state and multiply it by the initial probability. For the next observation, at each state, we will evaluate the probability that a transition has occurred from each of the previous states to the current state, multiplied by the probability of emission of the observation in that state and the pondering obtained for the previous state. Then we will choose the highest percentage for the current state and continue with the next one. Finally, we will select the state with the highest weight for each observation, obtaining the most probable hidden states and solving task 2. The final score obtained represents the value of task 1. For the observations made, the states obtained in our example are exploration, exploitation, convergence, and jump out. According to the classification of states made, we will update the value of the inertia coefficient and the particle number for each PSO individually. In the exploration state, we will decrease the number of particles. The inertia coefficient is stochastically updated to a value between the minimum and the maximum. In the exploitation state, we will increase the number of particles. The inertia coefficient will take a value between 0.4 and 0.9 in proportion to the value of the evolutionary factor. In the convergence state, we will increase the number of particles and decrease the inertia coefficient to a minimum. In the jump out state, we will decrease the number of particles and increase the coefficient of inertia to the maximum. The results obtained show a good behavior of the algorithm compared to the original algorithm. As the instances of the set covering problem contain more variables, the difference between the two algorithms become more noticeable, which shows that the adjustments made to the parameters allow the algorithm to find better areas in the search space and avoid local optimum. As the conclusion of the work, we note the following. The proposed improvement to the GSO algorithm is shown to be effective when compared to the original algorithm. The optimization of parameters shows a behavior capable of avoiding local optimums in which the original algorithm falls. In this presentation, we reviewed the integration of the Hidden Markov Model framework into the PSO algorithm for the deduction of its current state and subsequent parameter adjustment. We used the GSO algorithm to run multiple PSO instances in parallel, obtaining good results in the resolution of the set covering problem.